So welcome again to the OsmoDevCall tonight. I'm going to cover the SIMtrace2 project. I called it a tutorial, so it has some emphasis on practical bits. Nevertheless, there is slides and some theoretical background, of course. So there is a brief, well, or not so brief part about SIM cards in general. I will skip through the slides rather quickly. Nevertheless, I thought I leave the slides in case somebody wants to follow up in the slide deck later on and read up on that. So there's some terminology during this talk. I'm not going to read this slide from top to bottom, but of course we will be talking a lot about the SIM, the subscriber identity module, and its various incarnations, including the UICC, the USIM, the iSIM, and so on. Another acronym that might happen to come around is MS or UE. That's the phone or modem, and all the other ones I guess we can skip for now. So there's a lot of different standardization bodies that have standards that somehow relate to SIM cards. This is just a brief overview. I gave a talk on SIM card technology from A to Z a couple of years ago that has some more on the specs and details on SIM cards. So as I said, I will skip through those slides rather quickly. Just in general, the concept, of course, of the SIM card was to store the cryptographic identity of the subscriber inside a smart card, meaning that the identity can be migrated from one device, from one phone to another, which also means the user can swap identities by using different SIM cards in the same device, by alternating different SIM cards in a device. Today, of course, we have phones with dual and triple SIM and all kinds of bits. So that's the original SIM. Of course, the modern SIM cards have evolved quite a bit from that. We have cryptographic processor smart cards with various crypto in hardware, usually crypto algorithms. We have Java card support with a small Java virtual machine and runtime environment, multiple applications on those cards, and also the ability to download applets on the cards. So all of this added complexity in the cards, of course, means that also the protocol that we will look at in the protocol tracing becomes more and more complex. The basics of the cards, we have some kind of microprocessor with RAM, flash, and operating system, and it has an electrical interface according to ISO 7816-3. Which is the main protocol that the SIMtrace hardware and firmware implement to trace this communication that happens between the card and the phone. All of these smart card basics are general, irrespective to SIM cards. SIM cards are just one use case where smart cards are being used. The protocols describe, the protocol used for SIM cards mainly describes something like remote operations on the file system. So you can think of opening a file, reading a file, writing a file, something like that, plus a few non-file system related commands, for example, for authentication, but also for proactive SIM and advanced bits and features like this. Yeah, so we have a file system on the smart card. You can think of it like a hierarchical file system, like on a PC, with some different terminology. We have in MF the master file, which is the root directory. We have dedicated files, which are subdirectories, and then we have an entry file, which is the actual file containing data, of which there are multiple flavors. We have so-called transparent files. We have record-oriented files. The record-oriented come in different flavors again. There's also yet another new file system type, file type, the BER TLB files. I'll not go into the details here. And there are no human readable or human understandable string file names on the card. The card itself uses 16-bit file identifiers, or I think it's 7 or 6-bit short file identifiers, not 8, it's not even 8-bit. So all the communication uses these hexadecimal identifiers, and the symbolic human readable names are just something that exists off the card in the specifications. Yeah, so we have a file system hierarchy like this on the card, for example, the master file, then we have a DF Telecom, telecommunications related file, which then contains various EFs inside, for example, SMSs in the EF SMS, or the mobile subscriber telephone number, the MSISDN here in this EF MSISDN. And we have other DFs and EFs and so on the card. All of those files have various permission bits, read and write permissions, depending on who is using the card, whether it's the user that is identified by their PIN, or whether it's the operator, or whether it's an applet, or whether it's remote file access, and so on. The typical commands that we see exchanged between a SIM card and the phone are commands like those listed here. We have select, which is changing a directory or opening a file. So if you select a directory, an MF or DF, you basically just change the current working directory to that location. And if you select a EF, then you select that file, you basically open that file. And then there can be read commands, depending on the type of file. There are different commands. There are write commands, which are called update here for those files likewise. And yeah, pin-related commands here. CHV is a different, card holder verification is a different term, old-fashioned term for the pin. So you can enable a pin, disable a pin, change the pin. You can verify the PIN, meaning you enter it and thereby authenticate yourself to the card. You can unblock the PIN using the PUC in case the PIN was blocked. And last but not least, you can run the authentication that was present in GSM. All the later features for USIMs and so on, they are covered in a few slides. So this is still talking about the basic classic SIM card here. So the typical operations we see the phone perform is to navigate to some file using the selects on DFEF, authenticate using the user PIN if the user has entered their PIN, and then we have reading and updating files. For example, the IMSI is being read during startup. The SMS storage is read, the contact storage may be read. And then once the phone registers to the mobile network, it is receiving new session keys, and those session keys are then stored on the card using update commands over this SIM card interface. Also, information like the last cell on which the phone was registered is updated on the card during normal operation. So that's the kind of messages we expect to see when we look at the protocol trace. I'll skip a bit over some of the slides. In modern SIM cards, we now have multi-application smart cards, meaning that there is not just one application on the card, but multiple. The classic SIM is one application, but there are additional applications such as the USIM, the UMTS SIM, which was introduced with 3G, but it is still used in 4G and 5G. And each application is identified with an AID, an application identifier. And these application identifiers are well known, or at least the prefix to those. So the phone can say, I want to select any USIM application on this card, and then the USIM or the first USIM application on the card will be selected appropriately. So the USIM has hundreds of other files. Some have an overlap with the classic GSM, some not. And then for 4G and 5G, they didn't add new applications, but instead they added additional files and directories beneath the USIM application. So you can use a 4G network with USIM. There is no eSIM like an evolved. Well, there is an eSIM, but it's a different context. But there's no E in the sense of evolved because everything in LTE 4G is called E. So yeah, there is of course SIM cards for other use cases like Tetra networks or GSM Railway, which then each have their additional files or different files specified in the related specs. Again, I'll not cover that in more detail. What we also find on modern SIM cards is an iSIM application that's for IMS, the IP multimedia service, which is what is used for voice over Wi-Fi and voice over LTE calls, and voice over new radio in 5G. This iSIM application again has its own application dedicated file with a number of entry files underneath. Yeah. So if we want to analyze the protocol accessing all those files and performing authentication and so on, there is not much we could do until SIMtrace came around. The normal end user phones or cellular modems don't really give you much information about what is happening. On some devices, you may be able to enable a DIAC interface, and you may find some proprietary or open source tools to actually obtain SIM card protocol traces this way. But this is highly vendor dependent and typically rather locked down on a lot of devices. And of course, it's not an actual trace of what happens on the SIM card interface, but it is something that the software on the phone tells you is happening. So it could already be modified or somehow not transparent. The SIM card itself, of course, has no kind of debug interface. There's not some kind of diagnostic pads or an additional UART or something where you can get debug information. There is no way how to extract any information from the card itself. But since all of this communication between the SIM card and the phone is unencrypted, we can passively sniff or trace this information. There have been a number of commercial and proprietary solutions that are relatively expensive. Then in 2010, Kevin and we created the original SIMtrace device to have a low-cost open source hardware, open source firmware, and host software tool to obtain such protocol traces. Which brings us to the actual SIMtrace device, and I'm going to talk about the SIMtrace2 here, except on one slide where I will illustrate what this 2 means and what SIMtrace1 was. But the SIMtrace2 device is primarily used as a passive sniffer or tracer for this SIM card to phone interface. It works in a way that you insert some adapter cable that has a SIM card shaped part. You insert that into the phone or modem. You connect that to the SIMtrace device, and then your actual SIM card you insert into the SIMtrace, which has a built-in card slot. Then the SIMtrace is connected over USB to some host PC or embedded system, whatever, some USB host that can run Linux. And then you have a program called SIMtrace2 Sniff, which receives all of these traces that are passed over USB and encapsulates them in a specific format, which I will talk a bit about. And then you have 2 options at the moment for decoding this information. One is the Wireshark dissector, and the other one is PySIMtrace, which I will cover later. So the logical setup looks like this. You have some kind of phone into which you insert a flex PCB cable that connects to the SIMtrace hardware. And the SIMtrace hardware then has a SIM inserted and has a USB cable to your host, to USB host PC, embedded board, whatever it is. And all the communication between the phone and the SIM is passed through transparently, but logical protocol traces can be sent over USB to the PC, where some software such as Wireshark and the SIMtrace2 Sniff program can interpret this information. So if you set this up, it looks like this. So you have this flex cable here. This is still an old 2FF sized SIM card. There are flex cables for 2FF, 3FF, and 4FF for all the form factors. So nano, micro, all of the SIMs in different orientations, so that the cable can go left or up or down or right. And The flex cable connects to the flex connector here on the SIMtrace board. So this is the SIMtrace board here on the right-hand side, and well, you cannot see it very clearly, but there's actually a plastic SIM card with some metallic design inserted in the SIM slot here. So that's the SIM card, and this is transparently passed through the flex cable. And here we have this Atmel SIM3S microcontroller, which then obtains the protocol trace and can export it here on the right-hand side over the USB interface to your PC. So, quick historical intermission. This was the SIMtrace2. Before 2015, we also had a SIMtrace device that was just called SIMtrace. To clearly distinguish it, we now call it SIMtrace1 to distinguish it from the SIMtrace2. Hardware-wise, it's pretty much the same, but uses an older microcontroller. And the firmware was a completely different project that was a strange fork of another earlier project that has nothing to do with SIM cards. And SIMtrace1 by now is not supported anymore. There is, of course, still the firmware around and the host tools, but they're not maintained and not updated. I don't know if they even build on modern Linux. And if somebody really has old SIMtrace1 hardware and wants to use it, I would say the best course of action is to port the SIMtrace2 firmware to this older hardware. It shouldn't be that much effort, but definitely it is a much more complete and sane implementation of the functionality than the old firmware hack for SIMtrace1. And if you have hardware in front of you and you are not sure whether it's a SIMtrace1 or SIMtrace2 device, you just look at the marking on the chip, and if it says SIM3S, then it is a SIMtrace2 device, and it says SIM7S, then it's a SIMtrace1 device. Michaela mentions there's a regression from SIMtrace1 to SIMtrace2 regarding 5-volt phones. I'm not entirely sure that 5-volt was ever supported, even with SIMtrace1. It might be, but to my knowledge, it was never officially advertised or tested. So that may have worked. I'm not sure. Getting back to the SIMtrace2 hardware, so we have this SIM3S microcontroller, and why this specific microcontroller and not an STM32 or some other microcontroller that's around. The reason is that those microcontrollers have two UARTs that are compatible with this ISO 7816-3 interface. And they're not just compatible in a sense that they stated on the datasheet, but they actually work, much unlike many of the later Atmel microcontrollers, which claim they support ISO 7816, and when you try to use it, you regret that you ever started doing so because it's full of silicon bugs. So also the nice part about those specific UARTs in this microcontroller is that they can either be clock master, meaning a SIM card reader, or they can be clock slave, meaning a SIM card. Where many other UARTs that you find in other microcontrollers, they only support the card reader functionality because that's the usual way how you use a microcontroller. You want to talk to some external smart card. But it's rare that there is a use case where the microcontroller actually should behave like a smart card itself. But this is possible and works reliable with this old SIM3S series of microcontrollers. We have built an open source firmware. I will mention that in a short while. It does auto boarding depending on the clock signal. So it's unlike some of the very simple older smart card sniffers, which assume that everything happens at 9,600 bps or something like that. We really follow the actual clock signal, and we derive the baud rate from the clock signal. So also support this PPS procedure for higher baud rates. So it will follow whatever is the clock rate and the baud rate on the between the card and the phone. The schematics and layout of this device is open source hardware under Creative Commons Attribution Share alike. Here's the link for the repository and the directory. If you don't want to build it yourself from scratch, there are some made available by on the Osmocom webshop. The firmware that runs in the device is again open source, in this case GPL v2 licensed, and there are 3 major programs that are built from the firmware repository. One is the DFU firmware, which is basically the bootloader that we use. This bootloader allows us to quickly and easily update and change the firmware, the actual application firmware. So we basically split the flash memory into partitions. One is the DFU bootloader, and the other partition is the application. And in terms of applications, there's 2 that are supported and working. One is the trace firmware that you can run for passive protocol tracing, which is the main part of this tutorial today. There's also the CardEM firmware, which I'll briefly cover in one slide regarding physical layer card emulation and remote sim use cases. There are some other, in the source code, there are some other targets and applications for the firmware, but those are incomplete and not supported. So feel free to play with those, but that's basically you're entering uncharted territory there. Yeah, source code and binaries. So we build official binaries in our build systems for the firmware. Every time a new commit is made, a new binary is being built. All of these are released at this link. So you don't need to build it from source unless you want to. That's entirely up to you. This firmware now supports also other boards that have similar functionality, which I'll briefly cover as well here. Stay tuned about that. We have then the host software. That's sort of the last part. So we have the actual hardware, the firmware that runs on the device, and the host software. And the host software consists of 2 parts. One is a library called libosmo SIMtrace2, which really implements most of the functionality, such as talking to the hardware over USB and implementing the USB protocol that we created. And then there are some applications that use this library. These 3 applications that I listed here are not the only ones. It's just the only ones that are included in the SIMtrace2 software package. Since the library is installed, of course, other applications can also use the library. And the remote sim software from Osmocom is one of the users of the library that basically creates different applications using the same library. The source code URL is here. We also publish packages for a variety of distributions, mostly different versions of Debian, Ubuntu, CentOS, and SUSE. Likewise, as with the firmware, the software also supports other similar boards, the host software, like the NGFF CardEM and SysmoQmod. Okay, and now in terms of decoding, we have 2 options, but before we go there, I think this is actually a good time to switch to one of the demos. So yeah, I have my SIMtrace device connected over USB. I can quickly put this in the camera. So we have the SIMtrace device, which is connected to my laptop. I'm also attaching it to a modem. So we have, there's also a SIM card inserted. So basically we have the full chain end-to-end setup here on my desk. And one of the things you might want to do every time you use the device, at least for me, that's only every couple of months. And the usual first step is to update the firmware. So let's start with this task. I've already downloaded firmware images here. The firmware images have a certain naming scheme. It starts with the hardware name. In this case, it's the SIMtrace device. Then it is the actual build target of the firmware. And the third section is the memory to which this is linked, basically. So we have the CardEM firmware for card emulation, which we cover later. Let's start with the trace firmware for the SIMtrace hardware, and it is meant for being installed over DFU. So this particular file here, the SIMtrace trace DFU, plus the version name here, that's the version name from the Git repository. This is the firmware that we want to flash. And the flashing works using DFU, that's the USB standardized device firmware upgrade. So there's a tool called DFU util, and we can use -L to list the currently attached devices that support device firmware upgrade on this system. There's exactly one, that's the SIMtrace device. I know that because this is the USB vendor and product ID of the SIMtrace device. And in case you're unsure, you can always, for example, unplug, and it's no longer listed. So it's rather clear that the device that is listed must be your SIMtrace device. One thing that is generic to DFU is that before you do any flashing, normally you have to detach the device, which means you switch from the normal operational mode into the firmware upgrade mode. This is called detach. And if you do that and then you list again, you get the actual, let's say, partitions or targets to which you can write software or read software from. The one listed on top is just the serial number of the device. The second one is the flash application partition. This is where we want to flash the firmware. The third one is RAM. That's not really used. In theory, you could just download code into RAM and execute it, but we want to flash the actual application software. So what we do is we say DFU util, and we say -A1 because it's the alternative one. So the alternate function 1. So oops, -A1. And we want to download with uppercase D the SIMtrace trace DFU. And after the download, we want to reset the device. So we do this download this file plus reset the device afterwards. So, and we execute this, which downloads the file into the firmware. We've reached 100%. There is some error message here, but nevertheless, if we list again, we are in runtime mode again, not in DFU mode like here. And the device is re-enumerated. We can also do as USB. So we see here the Osmoco. Osmoco is the donor of the USB ID, so it's the Osmocom SIMtrace2 device. In the host utilities, there's a program called SIMtrace2 list. Yeah, sorry. I have, for development purposes, I have this address sanitizer enabled, which always gives a lot of additional information about memory usage and possible memory leaks. So I'm just redirecting that. So what we see here is the two USB interfaces, or rather the two configurations that are being offered by the SIMtrace device. We see it's only one device because it's the same address and the same path. It's just different configurations. And one configuration is the sniffer. The other one is just a way how we can expose the firmware build version that is installed on the device. So we see the device exists. It is attached. SIMtrace2 list recognizes the device, and now we can start the actual tracing process. So we can do SIMtrace2 sniff, which uses, if you only have one device attached, it uses the one device you have. If you have multiple SIMtrace2 devices attached, there's a number of options you can use to specify the USB address or the path or other parts of the USB configuration to select one of the devices that exist. So here we only have one device, and we start this and it runs, and that's basically it. What this now does is that all of the can we set, Max has a question, can we set SIMtrace instead of unknown name shown by DFU util? Actually, I don't know. where this is coming from. I mean, I did participate a long time ago in the development of this tool, but I don't recall where this particular name is coming from. But yeah, the source code is out there, so feel free to investigate if we can change that somehow. So what the SIMtrace2 sniff program is doing is it receives any SIM card communication between SIM card and phone, and then it passes it over the loopback device over IP, over UDP in the GSM tab format. GSM tab is a pseudo header, an artificial header that we introduced many years ago to encapsulate protocols that are not normally spoken over IP. We can encapsulate them over IP. So we can use standard tools like TCP dump to capture traces or Wireshark to decode traces. So basically, we take the SIM card communication, add this GSM tab header, put this in UDP, and we send this over a socket so that Wireshark, for example, can see the related traffic. So I'm going to start. No? If I can still type, we can start Wireshark. And we can run Wireshark over the loopback device. That's where we send those GSM tab frames. And now I'm going to power up my modem, which means it boots now. It takes ages to boot because it's a 5G modem, an early 5G modem that is particularly slow in booting. So it's quite normal that we don't see anything other than, well, what we already see here is that the card reset was deasserted and asserted again. It should be deasserted, of course. So basically, now it got the card out of reset and put it in reset again. So it needs to get it out of reset, and then we should see protocol traces coming up in a few seconds. Basically, whatever the modem is doing during boot up with this specific SIM card. And we will get a raw hex dump here on the console output of the SIMtrace2 sniff program, while then in parallel, it puts these in GSM tab frames. And if we look at Wireshark, we see the related or respective Wireshark decode of at least the very outer layer of this protocol. So we see that certain files are being selected and that files are being read and so on in this protocol trace. As you can see, it's extremely verbose and extremely lengthy, and even something as simple as, let's say, selecting the EFICC ID, that's the card serial number, the file, then there's a get response, a read binary. So we see already 3 lines just for reading one bit of information, which is the ICC ID in this case. Where is it? Select if there's the response, read binary. If you, there's the payload. Yeah. So this is basically the ICC ID of the card that's being read. But you see, it's a lot of churn, and the actual information. I mean, you only get a hex dump of the file itself, and then you need to consult the specification, like what is the format of encoding the actual ICC ID into the binary file, and need to manually decode that. It's not very comfortable. It was some very easy, very early, simple way of getting basic decodes. And unfortunately, not many contributions were made over the last decade to the Wireshark sector. So this decoding of the SIM card protocol is still extremely basic, to say the least. So yeah, that's it. There's not really much else to this. So this continues running. And now if we were to use the modem to make a call or to set up whatever, some data bearers or voice over IP or whatever, we would see additional communication here between the card and the modem. Now we don't, because it's just idling. It has done whatever was necessary during startup, and we don't see anything but this occasional command that we see repeated every couple of seconds here or minutes, what is that? We can have a look. It's the status command. Actually, let me filter on GSM. The proper filter, so we only see this information relevant to us. But yeah, it's a status command. This is basically just the modem polling the card, getting a status. It's like a keep alive or a handshake. Are you still there? What's your status request? Yeah, so that's the basic decoding with Wireshark. What's new now in 2022? I think it was this year. I created a better tool for looking at the decode. I already mentioned that the Wireshark decode is not particularly comfortable. And the actual interesting bits depends a bit on what you're looking at, but I would say for 95% of all use cases, you're really interested in the application layer communication and not in the lower level bits, whether the select file command is correctly encoded or something like that, but you actually want to see what is the logical content that is being read or written to the card, and not how is this encoded in hex and are the bits all correctly set. So the problem is that, of course, every of the hundreds of files has different content with different encoding and a different format. And putting all of this in Wireshark is not really a good fit from the architecture, because actually Wireshark is for decoding the protocol, and the protocol itself, it is decoding. But now, basically, we have an application that uses this protocol to read and write files, and we want to decode the structure of those files. And that's a bit like, yes, we're looking at a protocol trace of a Samba or NFS file share, but now we want to decode the JPEG or the CSV file that is inside, that's basically that is transported over this network file system protocol. It's a bit on that level, so it doesn't really match what Wireshark is doing. And what we meanwhile had created is the PySim software, and specifically the PySim shell software, which already contains encoders and decoders for most of those files, because PySim shell is what you can use to manually read and write SIM cards when you have them inserted in a SIM card reader. And now SIMtrace was sort of the logical next step, where we use all of this information on all of those existing decoders and encoders for the protocol, but we connect it to the protocol trace and not to an actual SIM card that we're currently reading. So SIMtrace is using all the libraries and the code base of PySim with its knowledge about the file system structure and file content, but attaching it to a decoder. And to show that, I will just unpower my modem again. I have one shell here in the PySim repository. There's this PySimtrace program. If I start it, it will just give me a syntax reference that I need to specify the format that it should consume. There is different protocols that it supports. In this case, we want GSM tab over UDP. Excuse me. So if we start this, we get some random output messages and entering main loop. So basically now it's waiting for, it has opened the GSM tab socket, and it's waiting for GSM tab encapsulated SIM card messages. And now we start again the SIMtrace2 sniff, which will complain that it cannot bind to this socket. That's normal because the PySimtrace has already created this socket now. So no, not a bug. And now I've powered up the modem again, and we wait until we see communication, which then again will show up as the hex dump in this output of SIMtrace sniff as before. Let's clear the Wireshark So we also get the same communication in Wireshark. And then here in this window where we have SIMtrace, we get the higher level decode of the communication. Yeah, I can already hear the power supply chirping at a different frequency. So any second now we should get some APDUs here. Yeah. So lots of stuff. I will just abort this here and scroll back a bit to the top. So we see here read binary, the path mf/ef ICC ID and the actual ICC ID that is being read from the file. And then as in the next line, we see read binary, the ef.pl, that's the language file. And here we see DEEN none, so German and English are the languages that the SIM card requests the phone to use. We see the status code here, 9000 is the standard OK code, so the operation was successful. Then we see a terminal profile and we see some managed channel and whatnot. But in any case, we get a JSON decode. It's not always very readable. If it's rather complex files like here, this EFUST, the USIM table that's being read. But for the smaller files, this works relatively well. So we see here location information, which MCC, MNC, TIMZ, keys, and so on that are being read here from this file. So the visual representation is certainly not the most comfortable representation that's possible. It was just all that I could do in the limited time, and I'm not a user interface guy, as those who know me know. But I think it is much more useful in many cases than the low-level decode from the Wireshark dissector. So, for example, here we only get one line read binary with the full path and the decoded payload and so on. Whereas in Wireshark, that would probably be 1, 2, 3, 4 select statements, each with a get response. So we're talking about 8 lines already, plus the read and response. So something like 10 lines in Wireshark are getting condensed into a more readable representation here. We see some warnings here. That means that the phone is actually trying to select an unknown file identifier. So apparently there are some non-standard files that this Quectel modem wants to open. Those are not specified by 3GPP, but apparently some vendor proprietary files could exist on a SIM card, and it tries to open them. But we don't support this, of course, in SIMtrace because we don't know those files. Here we see some red result codes. That's basically whenever it's not a 9000 OK code, you would have to check what this respective code means to see why and why this is a different code. I cannot tell you what 6282 is off my head, but it's not a standard successful code in any case. Okay, so that was the SIMtrace based decoding. Let's get back to the slides. Yeah, which brings us to the next topic that's possible with a different firmware, which I just very briefly cover here. The SIMtrace device, as the name implies, was meant originally for tracing communication. But with a different firmware, the same hardware can also emulate the physical SIM card interface, which opens up the option of passing or transparently transporting the communication between SIM and phone to a remote location that you somehow have connectivity to. The SIM card could be somewhere else. You could also run a complete software emulation of a SIM card if you happen to have one. There currently is no, there is an older open source project in Ruby from Kevin, but I don't think anyone has made that interoperate with the CardDM firmware of SIMtrace2. There will soon be a open source implementation of a full SIM and USIM. I cannot say more at this point, but we've been working on something, and it will be for a customer. It will be open source, and just the development of this couldn't be in open source because the customer wants to make some press releases and so on. But there will soon be a fully open source emulation for a SIM card that you could then run on the host against a SIMtrace device and without any physical SIM card. And you could use that to play with SIM cards in a different way. There is some projects related to this card emulation and remote SIM card forwarding. I'm just giving some references here. There's also an OsmoDevCall on that topic. In case you're interested in that, do check that out. There's also a couple of other hardware boards, as I mentioned earlier, that share the SIMtrace firmware and the SIMtrace host utilities. One is the Sysmo QMod board, which is a carrier board for 4 MPCIe modems, and it has 4 SIM slots, of course, and it has 2 of the SAM3S controllers, because each has 2 UARTs, so each of them can serve 2 modems. It does not have tracing support. It only has card emulation or card forwarding support, since that was what this board was designed for. It's not open source hardware, just mentioning it for completeness here. The NGFF card DM is the latest member of the SIMtrace derived hardware boards. This is again an open source hardware project. It is a carrier board for an M2 or NGFF modem. You see the slot here. There's no modem inserted in this picture, with a SAM3S and SIM slot. So basically, you can think of it as a modem carrier board for an M2 cellular modem with an onboard SIMtrace. And actually, something that's even better than a SIMtrace because it can do it has one UART connected to the modem and the other UART to the card, and it has switches in between, a switch matrix, so you can, the hardware is capable of doing tracing like SIMtrace. It's capable of doing card emulation or card forwarding like also SIMtrace. But you can also run at the same time, in theory, use this slot as a card reader, expose it to your PC, and use that part in card emulation mode. So you have a bit more flexibility there. It supports most of the modes, or basically all of the modes that are possible in theory. The firmware and the host software doesn't support anything but card emulation or SIMtrace, so it functionally, the complete system is equivalent to a SIMtrace, you could say, but it has this modem carrier built in. Yeah, so what is left as to-do items, and this has, all of these items have been left for more than 10, I think 12 years by now. In theory, you could use a SIMtrace and also this new NGFF card DM also as a smart card reader. We once had some proof of concept code for that, but it bit rot and it's no longer supported now. The point is that a smart card reader is so inexpensive that nobody has bothered spending time in like really completing the firmware for this, but the hardware is fully capable of doing so. And combining the card emulation plus the CCID reader, you could then do man in the middle APDU filtering. So you could basically pass some communication, but not pass other communication or manipulate communication between the SIM card and the phone. But apparently this was not attractive enough for anyone to, at least not in as open source, to implement those bits. The other bit that is not implemented is T1 protocol support. The cellular modems or the cellular SIM cards use generally T=0 protocol. That's one of the ISO 7816 protocols. And the other smart cards in general, such as crypto smart cards, banking cards, and so on, use T=1 protocol. That's a different layer 2 protocol, you could say, on top of the same UART and the same electrical parameters. That is not supported in any of the modes of any of our firmware at this point. Yeah, another option that's possible from the hardware side that nobody has ever implemented, we have an SPI flash on the board. So you could do some protocol trace recording to that flash chip without a PC attached, without any USB host. But yeah, it has never been, to the best of our knowledge, has never been used. At least nobody has ever contributed related code. What's the capacity of the flash? I cannot say off my head. I would have to check the BOM. I think a few megabytes, but yeah, 8 megabytes or something, I would say. But yeah, let's we could actually check the BOM maybe later in the Q&A section. Yeah, it's great. Michaela states they have a use case and might be interested in developing support for that. That would certainly be appreciated. Finally, making use of this underused, the most underused electrical component on the board for 12 years. Maybe some anecdotes around the history or the device itself. Originally, we developed this because we had a use case for it. We were interested in doing some security research. So we built this mostly for ourselves. And we, in this context, means Kevin and myself. And then, as usual, with those projects, we also make it available for other people. And it is the most surprising project. I'm not sure where we are in terms of serial numbers, but I think it's in at least 1,500 or 1,700 SIMtrace boards that Osmocom has built and sold. So apparently there are a lot of people out there who have a use case to trace SIM card protocols. I would have never expected that. When we started this project, I thought, there's maybe a couple of dozen people on the planet who might want to use something like this. I would have never imagined that we would go beyond 1,000 units on this. So yeah, big surprise. But then the other big surprise is, despite the rather large user base from those many units that we sold, and of course there might be many more units that other people have built. It's open source hardware. We didn't receive all too many contributions, unfortunately, to the project. Yes, there are some bug fixes here and there, and they're very much appreciated, but I would have expected, with so many users, there would be more contributions. But yeah, it is what it is. And with that, I'm opening the questions. This is now the first section for Q&A that are part of the recording. So if you have a question that should not be, or a comment that should not be recorded, please wait for a few more minutes until we stop the recording. So in case you're watching this video recording later, right now some people are typing in the chat. So Michaela says she is thinking of building a new hardware board with level shifters for 5-volt compatibility. That might make sense. I actually think that some of our other designs, maybe the NGFF CardIM, I would have to double check. So we have done a number of different hardware devices, and some of them use even a dedicated ASIC for like a smart card interface IC that supports all of those 3 voltages. But I think this is only when it's used as an actual card reader. So for passive tracing, you cannot use those. I would have to check if any of the existing designs have 5-volt support, but it never was a target for us so far. So I understand that there are some people who like to work with old phase 1 GSM phones that use 5 volt as the supply and logic voltage of the cards, but it is unfortunately it was too niche. Even 12 years ago, when we built it, I think we didn't really have at that time any phones that still used 5 volts as a voltage. Some of the boards that we did actually are more intelligent than the SIMtrace in that regard. So I think on the NGFF KDM and on the QMod, we would actually detect if 5 volt are being used because we have an ADC connected to the voltage, and we could basically not forward any attempt with 5 volt, trying to trigger the UE to switch to 3 volts if it supports that. But yeah, it's still not 5 volt support, of course. Kevin says, an SIMtrace upgrade for 1.8 volt for newer phones would be nice. Yeah, but the point is that all devices must support 3 volts, at least the latest 3GPP specs and ETSI specs that I'm aware of. Well, like the the UE must support 3 volt. It's actually 3 volt, not 3.3. Sorry for that. And the cards also must support 3 volts. So again, with the ADC, we can detect that only 1.8 volt are present, and we can not send an ATR or pass the ATR if 1.8 volt are being used. Yeah, Michaela, it's correct that the phone controls the voltage, not the card, but
it tries first it tries from higher voltages to lower voltages. So as soon as the card responds with 3.3 volts, then it will with 3 volts it will continue with 3 volts. So no need to go lower because the phones also support it. And all cards don't have to be damaged if they are talked with 5 volts. So
I think it's actually the other way around. I think they start with lower voltages, and the first voltage at which the card responds with an ATR then is used. But in any case,
right.
There is a handshake mechanism. Thanks, Kevin, for that comment, by the way. So this is the Kevin that I mentioned several times as the co-creator of the original SIMtrace device. Very happy to see Kevin is around here today as well. Okay, I have the feeling that we have a couple of very specific topics, but no general questions or comments. Does the decoder? Okay, that's an interesting question. Yet this the Ralph is asking whether the decoder already includes EUICC operations. There aren't really, as far as I recall, there aren't really anything. There isn't really anything new on the ISO 7816-3 or -4 level when it comes to EUICCs. In the end, it is just using envelope commands and existing commands that have existed for many years before. So this all happens at higher levels. So there isn't really anything that we would need to decode for EUICCs, as far as I'm aware. Basically, it's using some form of secure messaging, and then it's encrypted anyway, so you don't really see. Okay, Christian Vogel mentions the spy flash is actually a 2 megabyte, 16 megabit chip. So still, considering that the SIM cards themselves typically have 64K or 128K or something, so it should be sufficient for some storage of protocol traces, at least trace logs. Yeah. Yeah. Okay. I'm going to stop the recording now. We can still have more questions off the record and start the USSE part of the OsmoDevCall. Thanks everyone for the attention, and hope to see you soon again on the next recording.